Good evening, ladies and gentlemen. Welcome to Cass Business School. I'm Stephen Haberman, Dean of the school, and I'm delighted to welcome you here this evening to one of the Dean's lecture series. We're delighted to have with us as our guest speaker Nicholas Christakis, sociologist and physician, professor of social and natural science at Yale. I'm going to say a few words about Nicholas in a moment, but before I do, I'd just like to say something about Cass Business School for those of you who are not regular visitors to us. And for those of you who are regular visitors to us, you know what I'm about to say. Cass is one of the leading business schools in the UK and in Europe. We are very international, and as you can see, we're located on the doorsteps of the City of London, the global financial centre of Europe. We have more than 3,600 students studying undergraduate, master's, MBA, PhD and executive doctorate programs covering a range of disciplines from general management through to specialisms in banking and finance. And this is a particularly exciting time for Cass. We have just recruited over 40 new academics, including 18 new professors over the last few years, bringing in subject experts, many of whom have not only outstanding academic records, but also considerable professional backgrounds. My world is a world of rankings and league tables, so I'm going to bore you for about 30 seconds, if you don't mind. As an indication of our global standing, other people rank our finance research as number 3 in Europe, our banking research as number 1 in Europe, our actuarial science and insurance research as number 2 in the world. And something that I particularly am proud of, they rank our research for the impact that it makes on professionals and practitioners as number 2 in Europe. And just as 2 examples of this, in this week's Financial Times, on Tuesday, Andrew Hill gave prominence to the work of Professor Scott Muller and his team on mergers and acquisitions. And in yesterday's Financial Times, there was an article about David Blake's work on estimating the number of very old people in this country and the errors that have been made and the implications of those errors. I just have to make 2 housekeeping announcements. Please can you make sure your mobile phones are off or on silent. The parenthetical comment is that the reception in here is very bad anyway, but please would you mind just doing that. And should the alarm ring, please can we use the emergency exits at the back. There's not going to be a fire alarm. If the alarm does ring, it's the real thing. So the format for this evening is Professor Christakis is going to give us a lecture for about 50 minutes, and this will be followed by Q&A, which Amanda Goodall is going to lead. And then we'll have some drinks outside, and there'll be an opportunity for you to talk to Professor Christakis. So let me now tell you a little bit about our guest speaker. As you can see from the main slide, he's director of the Human Nature Lab at Yale. He's the sole Goldman Family Professor of Social and Natural History at that university. His current research is focused on the relationship between social networks and health, and it involves the application of network science and mathematical models, and I understand we're not going to see too much of the underlying mathematics, the application of those things to understand the dynamics of health in longitudinally evolving networks. He has degrees from Yale, 2 from Harvard, and 1 from the University of Pennsylvania. He has a very long CV. If you don't mind, I won't go through it all because you don't want to hear me read it. You want to hear him speak. But let me just say that he's a fellow of the American Association for the Advancement of Science. He's been acknowledged by Time magazine as one of the 100 most influential people in the world, and by Foreign Policy magazine as one of the 100 global thinkers, one of the top thinkers in the world. This is his title, Connected: The Surprising Power of Our Social Networks and How They Shape Our Lives. Also the title of a recent book that he's co-authored, which has been translated already into nearly 20 foreign languages. Please let's welcome Professor Nicholas Christakis.
Thank you very much, Dean Haberman, for that kind introduction, and Professor Goodall for arranging this invitation. So I'm going to be discussing today how and why we're all connected, and how and why social networks affect all kinds of different phenomena. And the kind of social networks that I'm interested in is the real face-to-face networks that we humans have been making for tens of thousands of years, ever since we emerged onto the African savanna. And not so much the more recent online variety, though I have a few things to say about that as well. So first of all, what's the difference between a group and a network? So here's a group of people. Every dot is a person, and there are 100 people over here. And we might describe a group as defined by an attribute, for example, Democrats or Republicans, or scuba divers, for example, or Manchester United fans. Or we might imagine a group as defined by a location. We might say those people over there are waiting to get into a theater, for example. But the difference between a group and a network is that a network, in addition to the constituent individuals, has ties, has the ties that connect the people. It has a specific number of ties and a specific pattern of ties among them. And there are two broad kinds of networks one can imagine: artificial networks and natural networks. So here, for example, is the simplest kind of artificial network you can imagine. We take those 100 people, we add 99 ties, and everyone is connected to the person on the left and the person on the right in the form of a bucket brigade. And this organization of these human beings gives this group properties that didn't previously exist, namely the ability to put out a fire, for example, more efficiently, or to empty out debris from a big hole. Or we could take the same number of people, 100 people, and the same number of ties, 99 ties, and arrange them differently, for example, into the form of a telephone tree. And for those younger than 25, this is an old technology that used to be used before the internet to notify people, for example, about a school closing. So the person indicated by the white arrow would be told to activate the telephone tree. They would have two people they were supposed to call. Each of those people had two prescribed individuals they were supposed to call. And this arrangement of the human beings, this topology, this network, was optimized for the rapid, efficient, accurate transmission of information. Incidentally, this same archetypical structure also lies at the core of Ponzi schemes, except now instead of information flowing from the center to the periphery, money flows from the periphery to the center. Okay? Or you can imagine now alternatives, which is not artificial arrangements of human beings, but natural arrangements. And natural social networks look completely different. They look like this. Once again, every dot is a person. Every line between them represents a relationship. And to my eye, social networks like this are intricate things of beauty. And they are so elaborate and so complex and so ubiquitous, in fact, that one has to wonder, what purpose do they serve? Why do we do this? Why do we humans, each of us inheriting our relatives, choosing our coworkers and our friends, in turn connected to other people who are behaving similarly, why do we assemble ourselves into a network with this particular structure? And to my eye, they are the human equivalent of ant colonies. They have this kind of ornate pattern that's highly reproducible in ways we'll be discussing today. And so the questions become, why are we embedded in networks? How do they form? How do they work? And how do they affect us? And I've spent the last 10 years or so thinking about how and why human beings form networks and how they affect many aspects of our lives: our health, our desires, our feelings, our thoughts, and our actions. And virtually all of the work I'm going to be presenting to you today is joint work that I've done with my long-term co-author and close friend James Fowler, who's at the University of California at San Diego. So I'm going to start with an example of obesity, not only because it's intrinsically important, but because it illustrates many of the important phenomena or key aspects of the kinds of topics that are of interest to us today. So first of all, as almost all of you are surely aware, the prevalence of obesity has been rising very rapidly in our society, and in the United Kingdom as well, from about 20% of Americans to 30% becoming obese even in the last 10 years, and fully 2/3 of Americans, about 66%, are currently overweight or obese. And it had become fashionable to speak about the obesity epidemic. And it's clear that obesity is epidemic in one meaning of the word, which is that there's more of it than there used to be before. But James and I began to wonder whether we could understand obesity as being epidemic in another meaning of the word, meaning that there was some kind of contagion, something that was spreading from person to person. And there have been numerous explanations advanced for the obesity epidemic that has occurred: the declining real price of food, the suburbanization of our cities, the change in the nature of work, the kind of the sedentary lifestyles that we've been adopting. And so we wondered whether we could add an explanation to all those other explanations. And to the extent that obesity is a product of personal choices and voluntary behaviors, the fact that people are embedded in social networks and are reasonably to be expected to be influenced by the behaviors and thoughts and actions of other people to whom they're connected suggested to us that it should be possible to discern evidence that weight gain in one person might be associated with subsequent weight gain in other people to whom that person was connected. So in order to study this, we had to assemble a kind of data that didn't previously exist. This is a large, prospective, densely interconnected social network of 12,000 people. And these are real face-to-face interactions. This is not online interactions. So every dot is a person, every line is a relationship. Who's whose friend, who's whose sibling, who's whose spouse, whose coworker, and whose neighbor, for example. And we did this by computerizing some paper records at the very famous Framingham Heart Study, records that had not previously been used for research purposes, which we realized contained this type of social information. And so we painstakingly computerized these records and reconstructed the network graph of the Framingham Heart Study, and then were able to take advantage of the fact that the Heart Study for decades had been collecting information about these people. So there are 2,200 people shown here. Every dot is a person. Now we make the dot size proportional to people's body mass index. So bigger dots are bigger people. And in addition, we color the dots yellow if the BMI is above 30. If you're properly clinically obese, we also color the dots yellow. And if you look at this image, you might be able to see that there appear to be clusters of obese and non-obese, yellow and red dots within the image, consistent perhaps with this idea that there might be outbreaks of obesity. But the complexity is still very high, visually speaking. And in any case, even if you grant me that you can see these clusters, there's many questions raised by this. First of all, how much clustering is there? Second, is there more clustering than simply due to chance? And third, how big are the clusters? What's the radius of the clusters? And fourth, and most important, what might be plausible causes of these clusters? So the first thing we had to do was to develop evidence that these clusters were more than chance and measure the radius. And so we borrowed some ideas from statistical physics, and we did a so-called topological permutation test, which yields results what are shown on this slide. So on the y-axis is the increase in the probability that a person is obese, given that a social contact of theirs is obese. And on the x-axis is the degrees of separation between the two people. So the first purple bar says that if your friends at 1 degree of separation are obese, you've got a 45% higher likelihood of being obese yourself. And the second bar over on red, if your friends' friends are obese, you've got a 25% higher likelihood of being obese yourself. And the third bar over in orange, if your friends' friends are obese, you've got a 10% higher likelihood of being obese yourself. And it's only when I get to your friends' at 4 degrees of separation that there's no longer a relationship between that person's body size and your body size. So if I knew nothing else about you, then the body size of this individual, who's almost certainly a stranger to you, your friends, for instance, I would be better than chance able to predict your body size. So this analysis says two kinds of things. First, it says that there's more clustering than due to chance. If it were chance, there'd be no excess risk. There'd be 0% across the board as you moved every geodesic distance, every step in the network, every step in the graph, for 1 degree of separation, 2, and so forth. As you moved every geodesic from the individual, there'd be no excess risk. Obesity would be smoothly distributed in the social graph. And so it's not that way. They're clusters. And second, it says that the radius of these clusters is to 3 degrees of separation. But it doesn't tell us what causes the clusters. And for this, we have to begin to think about other sorts of things. So there are at least 3 possible explanations, here doubled, for the clusters. The first on the far left is this idea of a social domino effect, or induction, which is the idea that as Amanda gains weight, it makes me gain weight. As I gain weight, it makes Dean Haberman gain weight. And so there's a kind of spreading process in the network. So one person's weight gain contributes to the next person's weight gain, and then it flows and cascades by a process of social contagion through the graph. A second possibility is not that my weight gain causes her weight gain, but rather that she and I form a relationship to begin with because birds of a feather flock together, or homophily, or love of like. Here the idea is that we have a similar body size to begin with, or a similar taste in exercise or in foods, and it's that causes the association between our weight. And the third possibility, or contextual factors, is that it's neither that her weight gain causes my weight gain, nor that we form a connection because we have a similar body size, but rather that we are jointly exposed to something like a gym that makes us both lose weight, or a fast food joint that makes us both gain weight at the same time. Now, typically, all three of these processes are present in any kind of social phenomena. So if you're interested in why your teenage kids are good students, is it that their friends are good students? Are they already hanging out with other good students? Or do they have a charismatic teacher that's making them both want to be good students at the same time? Or if you're interested in whether iPads are selling, is it that people are affected by what their friends are buying? Do technophilic individuals preferentially form attachment with technophilic individuals? Or is Apple's marketing campaign particularly effective, and that's what's, regionally within the graph effective, and that's what's making the clusters? So it requires a variety of econometric and eventually, as I'll show you, experimental techniques to disarticulate the extent to which each of these phenomena is true. And we used a variety of statistical and conceptual approaches to get a handle on this in our setting, a variety of so-called identification strategies. And in particular, one idea that we were able to exploit is that we had longitudinal information about our data. So we could trace out whether weight gain in one person was associated with weight gain in others subsequently in time. And in addition, we wondered whether we could visualize the spread of obesity. Was weight gain in one person associated with weight gain in others around them at a subsequent time period? And this was complicated because we needed to take into account the fact that the network itself was changing across time. Both the structure of the social graph was changing, and the attributes of the individuals were changing in complex ways unfolding across time. And so we decided to borrow some ideas from physics again. So many of you may remember in high school doing an experiment where you have a water table and you assemble an apparatus and you drop a marble into the water, and if you do it just right, the water will create waves that go out to the periphery and hit the perimeter of the box and bounce back, and you'll get standing waves on the surface of the water. Or if you don't remember that experiment, you'll remember being a child and sloshing your body around in the bathtub, and you know if you slosh your body just right, you'll get a big wave of water that comes out of the bathtub and goes onto the bathroom floor. So what we were wondering is, could we see evidence for a wave of obesity in this social network? Could we see evidence that as I gained weight, it made my friends gain weight, and as my friends gained weight, it made my friends' friends gain weight? Could we see this wave spreading on this hyperdimensional surface that is a social network? So here the network is rendered in 2 dimensions, but actually it's an n-dimensional object that's now flattened out, just like you take a photograph of a building, which is a 3-dimensional object, and you can flatten it out. You can have different photographic renderings of a building. The building is the same building, no matter how you render it, but of course you can take a picture and render it in 2 dimensions. So could we see these waves? So I'm going to show you now a little 30-second video animation of real data that took 5.5 years of my life and $1 million to make. And my children joke that on a per-second basis, this is much more expensive than Avatar and much less interesting, and they're right. So when James and I first had this idea in 2001, we thought we might explore this topic. It took us a couple of years to get the funding to do this, then a couple of years to build the data set in the archives of the Framingham Heart Study, about a year to get the statistical software to work, and another 6 months to get the video animation software to work. And when we did this at the time, the status of the field was primarily to take photographs of networks, static images. There were very few, if any, movies of networks like what I'm about to show you. And this, in fact, we've made many since then. This is, in fact, the first video we made of anything, and it shows the spread of obesity in the network. So every dot is a person. The red perimeter dots are women. The blue perimeter dots are men. The gray lines show spousal connections, and the purple lines show friendship connections. So here we only show non-genetic types of relationships. So 2 people connected by a line who have a similar body size, it's not because they're parent and children or siblings. These are social relationships between spouses and friends. Again, the dot size is proportional to people's body mass index, Bigger dots are bigger people, and the yellow dots, we color them yellow. The yellow dots are people who have BMIs above 30. So I'm going to put this network into motion in just a second. We're going to take daily cuts through the network for 32 years, every single day evaluating the status of the network. Now, we don't weigh everyone or assess their social relationships every day. This happens roughly every 4 years, but it happens on different dates for every person. And on any particular date that something happens, things are going to happen. You're going to see them happening. So for instance, people will be born and die. Dots will appear and disappear. You're going to see ties form and break as people marry and divorce each other, or friend and defriend each other. This is the real old-fashioned defriending, not the Facebook defriending, where people cut the ties to each other. You're going to see dots get bigger and smaller and turn yellow in color. But mostly you're going to see a sea of yellow as the dots become yellow in the time period between 1971 and 2002. Now, when you look at this image, I want you to think about whether you can see this wave of obesity or not, and be honest. So here we go. It's like a living thing to me, this thing. This is what we do, we humans. We make this graph, and it rewires, but it has a coherence and a stability, which is also a topic of conversation. In a moment, you're going to see this woman here gain a ton of weight. There she goes. She's going to move to the middle of the graph, kind of causing obesity everywhere around her. Now we're at the peak upswing of the epidemic, so we're going to see a sea of yellow that's arising in the graph. Now we're approaching the end of the animation. Now be honest. Did you see this wave of obesity or not? We didn't see it. We were so depressed. I mean, this was both the most exciting and the most depressing moment of my scientific career, because we had spent 5.5 years, James and I, and we sat at the computer and we were convinced we were going to roll the video, which we had painstakingly coded, and see this wave. And we played the video and we didn't see it, and we played it again and we still didn't see it. And it took us a whole day before we realized the error in our thinking. Now, usually in an audience this size, there's someone out of 100 or 200 people, one person quickly can figure out in a day what it took us 2 days. Any ideas as to why this wave is not apparent? Any thoughts?
Keeps breaking on itself in little pieces.
Say that again?
Keeps breaking on itself in little pieces.
Okay, so the suggestion here is that it's something to do with the evolving topology of the graph, that it's fragmenting and reassembling. And that's a good thought, but that's not the reason you don't see it. It increases the visual complexity, yes, but that's not why.
This is geographical, right?
No, it's not. This is arbitrary space. So this is just like a photograph of a building. There's a complex algorithm called the Kamada-Kawai algorithm, a so-called spring embedder network. What it does is, it's interesting, it treats each tie as if it's a spring, and then it iteratively repositions the nodes in two-dimensional space in keeping with Hooke's law, another thing from high school or college physics, famous Brit competing with Newton, spring constant. And it positions the nodes to minimize the energy in the system, but it's arbitrary. The network has a topology that's invariant, but it's arbitrary. That's a good thought too, yeah.
Could it be that they're overlaying waves, so it might
Yes.
be marble, sort of already shadow going from the side?
Yes, exactly. And it took us a whole day to think of that. So it's not a single hand dropping a single rock on the surface. It's a whole handful of rocks being thrown on the surface. So every rock falling, plunk, 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 creates these waves, but the waves interfere with each other. You've got wave interference on this socio-topological surface. So you need a different set of mathematical tools to back out to see. There are waves from each pebble falling, but you can't see them. It's like if you look out at a bay and you see lots of boats coming in, each boat is leaving a wake, but the wakes interfere with each other, so you get choppy surface. You don't see the wakes. You just get chopped. So the question is, can you use other techniques? So we did those kinds of techniques, and eventually we were able to persuade ourselves that there were these kinds of waves happening in the graph. And we were able to discern evidence for interpersonal influence across a host of types of ties between friends and siblings and spouses and coworkers. And we found that both weight loss and weight gain can spread in the network, such that if your friends or your friends' friends gain or lose weight, it affects you. And there were a variety of mechanisms by which it might do so, we concluded, including a spread of norms about acceptable body size. So it's not just behaviors that are spreading, it's ideas that are spreading. As your friends gain weight, it changes your ideas about what an acceptable body size is, and then you gain weight and pass that idea on to the next person. And eventually we started to look at other sorts of phenomena, for example, such as human emotions. Now, when human beings have emotions like anger or happiness or fear or disgust, we show them. Why? Why do we show our emotions? Even Brits. It's not hard to construct an argument from evolutionary biology as to why people would feel emotions, why it would increase our fitness as an organism to experience emotions. But not only do I experience an emotion, but I show it. And not only do I show it, but you can read it. And not only do you read it, but you copy it. It would seem that emotional contagion was a very deep and fundamental aspect of human emotional experience. And this function of emotions suggests that whatever other advantages they offer, they're also a primitive form of communication. Now, we're accustomed to thinking about emotional contagion as fleeting and involving just a pair of people. So a few years ago, I presented this work on emotional contagion in New York City, and I said, you know, when you're on the subway and the person across the car from you smiles at you, and you just instinctively smile back? And they said, we don't do that in New York City. And I said, well, everywhere else in the world, that's normal, except London perhaps also. It's normal human behavior. So we're accustomed to thinking about this. And Jane Goodall's work on, for example, how chimps communicate emotionally is in keeping with this idea that there's something instinctual in fleeting emotional contagion. And we're also accustomed to thinking about broader and collective expressions of emotions, but that are punctuated in time, like riots, for example, which reflect anger. But we wondered whether emotions might spread beyond pairs of people, and might they do so in a more sustained way than riots? Could there be a kind of a quiet riot? Could there be a kind of emotional stampede rippling below the surface of the human social fabric? And could we borrow ideas now from zoology about stampeding and herding behavior in animals and begin to apply that to understand this type of phenomena in humans? Maybe emotions spread across network ties well beyond pairs and in a more sustained fashion all the time. In fact, maybe emotions have a collective existence and not just an individual existence. So we created what I am pretty sure is the first network map of human emotions, published in the British Medical Journal a few years ago now. Every dot is a person, the square dots are men and the round dots are women. Now we color the dots using a validated psychometric scale that other people developed. The yellow dots are happy people, the blue dots are sad people, and the green dots are in between. And if you look at this image, you should be able to see clusters of happy and unhappy people within the social graph. And these clusters, again, spread to 3 degrees of separation. And similar analyses to those that we did before for obesity documented a role of induction in this type of emotional contagion, a spreading process of induction. It's not just that happy people hang out with happy people, they also make each other happy. Now, if you look at this image, you also might be able to begin to discern something else, which is that structurally the blue dots are more likely to be located on the periphery of the graph, and the yellow dots occupy more central locations within the network. And this allowed me and James to return to another high school topic of ours, which is the endless arguments we had with our mothers about why we were so unpopular in high school. Because James and I, independently, James grew up in Oklahoma, I grew up in Washington, D.C., we obviously didn't know each other, but we were both very nerdy. We would bemoan to our mothers that if we could just be more popular, we'd be happier. If we just had more friends, then we'd be happier. And our mothers would say to us, if you became happier, then you'd have more friends. So about 30 years later, and many graduate degrees, and $1 million later, we were finally in a position to test whether we were right or our mothers were right. And on this rare occasion, we were right and they were wrong. It turns out that being located in the middle of the graph is more likely to be associated with whether you become happy, with whether you are happy is likely to be associated with acquiring a central position within the graph. Now, the projects I've shown you so far have used observational data and have not involved any kind of experiments. So while they're very realistic in describing the world, they have problems of causal inference. It's difficult to be certain as to what is causing what. And partly to address this concern that we had, and also prompted by our work on emotions to begin to dig deeper into the deep causes or reasons why we make networks, we began to do some experiments, creating artificial networks in order to study. This is one experiment we published a few years ago in PNAS. Here in this experiment, Swiss college students were brought into the laboratory and were randomly assigned into groups of 4 strangers. They didn't know each other from before. And they were each given a little bit of money, and they were told to play what is known as a public goods game, where they can contribute a little money to the collective. If they did, the investigators multiply that money by 2 and divide it out to the 4 participants. From the individual's point of view, the best thing to do is to defect, not to contribute and hope that everyone else contributes. But of course, if everyone defects, the group suffers. And the best outcome is if everyone cooperates. And then a bell would ring and people would be randomly assigned to new players, new participants. And then a bell would ring and they'd be randomly assigned to new ones, and so forth and so on for 6 rounds of gameplay. And what we realized is that it's possible to use that data to reconstruct a network of interactions. So here what we're interested in is the following question. Not, if I am kind to Amanda, does she reciprocate the kindness and is kind to me? That's known as direct reciprocity. It's actually a difficult and interesting topic in the social and biological sciences, why we're altruistic to each other at all. It's deemed as a fundamental threat to the Homo economicus idea that we're all selfish. We're not all selfish. Why is that? And there are various accounts that have been given by a number of scientists about direct reciprocity. Another topic is indirect reciprocity. I'm kind to Amanda, and then you are kind to me, okay? And there are a number of ideas as to why that might take place. For instance, that you see that I'm a kind of guy, and that I might reciprocate to you. What we were interested in is not that, neither direct nor indirect reciprocity. What we're interested in understanding is that if I'm kind to you, do you then go on to be kind to him? And does he then go on to be kind to her? Could we discern a kind of a contagion of kindness in the social graph, here assessed experimentally, so there's no question that homophily or confounding might have caused it. It had to be experimentally induction. And that's exactly what we were able to find. We were able to show that if Eleni is kind to Lucas in period 1, highlighted in red, Lucas is kind to Erica in period 2, Erica is kind to Jay in period 3, and Jay is kind to Brecken in period 4. There's a geodesic spread of kindness here shown experimentally. And this is one of the most bizarre results to come out of my lab in the last 5 years. Because what I've just told you is that how Jay treats Brecken depends on how Eleni treats Lucas, even though neither Jay nor Brecken ever saw or interacted with Eleni or Lucas. How you 2 people treat each other depends on how those 2 people treat each other, even though you guys don't know who those guys are. So there's a kind of pay it forward phenomenon that takes place in social systems, whereby altruism and its opposite also ripple through the network. And this geodesic spread of kindness is different than the temporal persistence of kindness, such that if Eleni is kind to Lucas in period 1, he learns to be kind, and is kind to Erica in period 2, and Lysander in period 3, and Bemi in period 4, and so forth. In fact, if you add back all the downstream kindness, for every extra dollar that Eleni gives Lucas, the network functions as a kind of magnifying glass, a kind of matching grant, doubling the downstream benefit from that initial action. So it's clear that networks function in this way and can have this magnification property, and pay it forward is real. So things spread in networks, and we and others have shown this for a variety of non-obvious phenomena. I've shown you a little bit of work about obesity. We've also done work on smoking, drinking, and drug use behavior. I showed you a little work on happiness. We've also done some work on loneliness and depression. I just showed you a little work on altruism. We completed a huge experiment last year on voting, randomly assigning 61 million people to a treatment of whether they're told whether their friends vote or not. We've also done some work on exercise, purchasing behavior, and we and others have done work on all of these topics and on ideas. And all of these things seem to spread to 3 degrees of separation. And that's just a rule of thumb. We have a number of ideas as to why it might be 3 degrees. And the simplest idea is just simple decay, like a children's game of telephone, that as things move through the system, they decay. And again, invoking the physics metaphor, you can imagine that if you drop a pebble on a surface, the wave doesn't cover the whole planet. It decays because energy is lost in the friction of the water molecules. And so there can be a social decay as well in social contagions as things are transmitted from person to person. And I should emphasize that not everything spreads, and that not everything that spreads by the same mechanism. So just because we use the word spread doesn't mean they all happen in the same way. Germs spread differently than ideas, which spread differently than emotions, which spread differently than money, which spread differently than behaviors. Different things spread in different ways. And both good and bad things can spread, not just good things. And a key idea about networks is that networks magnify whatever they are seeded with. Networks magnify whatever they are seeded with. The networks don't care. They will magnify Ebola and fascism and violence, but equally they will magnify love and kindness and happiness. But they must be seeded. The network on its own doesn't give rise to the phenomenon. There has to be an exogenous force, a hand dropping rocks, that drops the rock onto the surface, and then you get the waves. So people's attitudes, decisions, and behaviors depend in quantifiable ways on the attitudes, decisions, and behaviors of others. Now, our work with emotions and with altruism got us to thinking about the fundamental reasons that humans form networks and whether this tendency and the tendency to form particular kinds of networks might be partially genetically encoded. Now, whenever human social networks have been mapped, they always kind of look like the images that I just showed you for the last few minutes. But they never look like this. Why not? Why don't we go out into the world, map a network, and find a network that happens to look like a regular lattice? It never happens. The striking pattern of human social networks, their ubiquity, and their apparent purpose beg the question of whether we evolved to have networks and to have particular kinds of social networks in the first place. So now the questions become, why do we form social networks in the first place, and why do they have the structure that they do? Now, to understand this, we need to dissect network structure a little bit first. So first of all, notice that in this type of a network, every position is isomorphic to every other position. Everyone has 8 friends, every one of their friends has 8 friends, and if you took this surface and you wrapped it around the surface of a sphere in 3 dimensions, or actually more properly a torus, a donut, every position would be equally peripheral and equally central. There'd be no one in the middle or in the center of the graph. But of course, that's not what real networks look like. Real networks have different positions. And there are a number of ways you can quantify this. Let me introduce 3 ways. So one very simple and obvious way is known as the degree of a node. So node B has 4 connections. This is a real network of college students and their friends. Node B has 4 friends, and node D has 6 friends. And people know this about themselves. You have 10 friends. You have 8 friends. I have no friends. People know this about themselves. But now look at nodes C and D. C and D both have 6 connections. And if you talk to them, this might be the limit of their understanding of where they are in the network. They have 6 friends. But we, with this bird's eye view, can see that C and D occupy different positions within the graph. And I can cultivate this intuition in you by asking you, who would you rather be if a deadly germ like Ebola was spreading through the network? Would you rather be C or D? D. Right? You have the intuition that D is going to be less likely to get whatever's spreading and less likely to get it early in the course of the epidemic. Now who would you rather be if a juicy piece of gossip were spreading through the network? C, right? And this can be quantified mathematically using something like eigenvector centrality or betweenness centrality, a contagion that begins stochastically within the network somewhere and begins to move randomly is going to reach node C sooner and is going to be more likely to reach C than node D. And this is known as the centrality of a node. Finally, look at nodes A and B. A and B both have 4 connections. But the difference between the two is that the friend of A's is back again a friend of A's, whereas the friend of B's is not a friend of B's. So in A, your friend's friend is your friend, whereas in B, your friend's friend is not your friend. Now, and this is known as the transitivity of a node, or the triadic closure. Now imagine that you were a prehistoric human and you needed to work together with your friends to kill a mastodon. Do you have an intuition as to whether it's better to be A or B? A. You're going to work as a team with your colleagues. You're going to go out, you're going to kill the damn thing. Now imagine if instead of the challenge being to kill the mastodon, the challenge was to find the mastodon. Here it turns out it's better to be B, because in A's case, your friend's friend is your friend. Do you know where the mastodon is? No. Do you know where the mastodon is? It comes right back to you. Whereas in B's case, you can reach further into the graph to get information about the location of predators or prey. And when we published a paper a couple of years ago now where we looked at the heritability of these 3 traits, so on the y-axis is the percent of the variance explained, or how heritable they are, and on the x-axis is the 3 features I just described for you. And on the far left, what we found is that 46% of the variation in how many friends people have can be explained by their genes. Now, this is not a very surprising result. Anyone who's lived in the world knows that some people are born shy and some people are born gregarious. People vary in their taste for friendship. And it's partially culturally determined and partially inborn. But now we also found that 47% of the variation in the transitivity of a person can be explained by their genes. This is another one of the most bizarre results to come out of my lab in the last few years. Because what I've just told you is that if you have Tom, Dick, and Harry in a room, whether Dick is friends with Harry depends not just on Dick's genes or on Harry's genes, but on Tom's genes. Whether these two guys are friends with each other depends on this person's genes. How can that be? Well, we think the reason is that people vary in their tendency to introduce their friends to each other. Some people knit the network around them together, and some keep their friends apart. And finally, 29% of the variation in how central you are also can be explained by your genes in a way we can discuss later if you're interested. So the fundamental reality of our desire for connection and our susceptibility to influence, it turns out, has always been with us. Where you are in this vast fabric of humanity depends in part on your genes. And the structure around us affects our interactions, but in a number of important ways. Now, if network structure is partially heritable, partially depends on our genes, and if it has evolutionary significance, it suggests that if we could go back 10,000 years in time, humans then should make networks very similar to the networks we make today. Now, of course, it's not possible to do that, so we came up with a slightly different strategy, which was to map the social networks of populations that live on the planet today like we did during the Pleistocene. There are very few such populations left, but the Hadza, hunter-gatherers of Tanzania, are one such population. And so we published this paper in Nature a couple of years ago now, and what we came up with the idea was to map the social networks of the Hadza. There are only about 1,000 Hadza left. Only about 500 of them live in the traditional way, and about half of those are adults. So we made a photographic census of the Hadza, a kind of Hadza Facebook, and in collaboration with Corin Apicella, who's the postdoc shown down at the lower right, and Frank Marlowe, one of the world's leading ethnographers of the Hadza, and again James, we sent Corin into the field with these posters of all adult Hadza, and every adult Hadza we could find, we asked them in a variety of ways to identify their friends. And then when we mapped the resulting network of the Hadza, we found that it looked just like ours. Visually and mathematically, with everything we could throw at it, their networks were indistinguishable from modernized networks using modern technology. So even though in the intervening 10,000 years we've invented agriculture, we've invented cities, we've invented telecommunications, we're still bound by this very ancient past, assembling ourselves into networks with fundamental, deep mathematical, biological, and sociological properties that can be discerned. So all of our modern technology is grafted on top of this fundamental, relatively invariant set of properties. Now, to be clear, we're affected in another way by social networks. It's not just what's happening around us that matters, the actual structure of the network also matters. Now think about these two objects, which, once again, we all studied in high school chemistry. As you all know, these objects are both made of carbon. And on the left, you have graphite, which is soft and dark. And on the right, you have diamond, which is hard and clear. And there are two key intellectual ideas here with respect to the allotropes. These are two allotropes of carbon. The first idea is that these properties of softness and darkness and hardness and clearness are not properties of the carbon atoms. They are properties of the collection of carbon atoms. Assemble the carbon atoms one way, they're properties of the collection of carbon atoms. And second, the second idea is which properties you get depends on how you connect the carbon atoms to each other. Assemble them one way, you get one set of properties. Assemble the carbon atoms another way, you get a different set of properties. And similarly, it's the pattern of our connections that affects the properties of our social groups. It's the ties between people that make the whole greater than the sum of its parts. Just like the bucket brigade and telephone tree example I gave earlier, you can assemble the people into one topology or the same people, the same human capital, into a different topology, and those resulting groups have different collective properties. New properties emerge because of the connections, because of the ties between people, and not necessarily because of the people themselves. So it's not just what's happening in the people around us, whether they are kind to us or happy or losing or gaining weight, for instance, that matters. It's the actual structure of the ties around us that also matters. One of my favorite examples of this was illustrated by my colleague Brian Uzzi, who's at the Kellogg School at Northwestern in Chicago, at the business school. Brian became unaccountably interested in the success or failure of Broadway musicals. So he assembled a data set of 326 Broadway musical production companies, the director, the producer, the musicians, the actors, and so forth. And he mapped the networks of the Broadway musical production companies, and he computed a quantity known as density that's very similar to the transitivity idea I introduced earlier. And so what he did is that he looked at the networks of the Broadway musical production companies. Here's a cartoon of one such possibility. There's 6 people. The person in the middle is connected to 5 people. Among those 5 people could be 5 times 4 divided by 2, 10 possible connections, none of which exist. So there's 0% density here. And here, 4 of the ties exist, so 40% density. And here, all 10 of the ties exist, 100% density. And then Utsi plotted on the x-axis the density, and on the y-axis the success rate of the Broadway musicals, computed either as the fraction of positive reviews or as the amount of money that the musicals made. And he found that if nobody had worked together from before, the show was a flop. And he found that if everybody had worked together from before, the show was a flop. And optimal performance was achieved when you had a mix of people, some of whom had worked together from before and some of whom had not. So if you want to kill a mastodon, you need some people who can find the mastodon and some people who can work together to effectively kill the mastodon. Optimal performance in this type of setting is achieved in this parabolic way. So the organization has value. Organizational networks have relevance to everything from productivity to innovation to cooperation and to all sorts of other features, some of which I have described and some of which I'm about to describe. Now I have I'm going to tell you a little bit of some work that we've done. I have 3 more things to discuss. One has to do with online networks. The second has to do with an experiment that we did, a couple of experiments I'll show you, and then I'll close with one big idea. So marketers, policymakers, epidemiologists, and business people, and others are beginning to wonder, does the online world resemble the offline world, and how is it different? Do things spread online as they do offline? So here's a natural social network of about 100 and so close friends within a college dorm. These are college kids. And on average, each of these kids has 6.5 real friends. And here's what happens if you add in blue, whether they're roommates, or in green, the green ties, whether they are members of the same club. And here's what happens when you add Facebook friends in red. So on average, and when we did this project 7 years ago now, they had 6 real friends and 110 Facebook friends. Now they'd have an average of about 400 Facebook friends. And here's what happens when you expand to all 1,700 kids in this college class. You get a tremendous amount of complexity, like this knotted bowl of spaghetti. And we wanted to understand whether the kids' interest in music or movies or books influence the friends around them. Could we find evidence for the spread of tastes in music, movies, and books within this social network? So for example, when it came to movies, here is the top 10 movies, most popular movies amongst these college students. And we found that if one of these students' tenuous Facebook friends, one of their sort of acquaintances on Facebook, expressed an interest in one of these movies, it had no effect on whether the kid was in the future likely to express an interest in one of these movies. But if we looked at one of their real friends embedded within the social network, within the online network, in the Facebook network, one of their 6 real friends, if he or she expressed an interest in one of these movies, it did affect them, but only for these 3 movies: Good Will Hunting, Pulp Fiction, and Love Actually. And then when we mapped the graph, and we highlighted the yellow fans are the Love Actually fans, the red dot are the Pulp Fiction fans, and there are only 2 fans of both, shown in orange, who occupy a position in the network right here between the 2 populations. We found that these populations were very segregated in the network. And now businesses often think that in order to maximize uptake of an intervention they're delivering into a population, what they need to do is identify central people and target them. But if you were actually selling Love Actually and you targeted the central people in this graph, you'd be out of luck because they wouldn't be interested in what you were selling. So you need information both about the social structure and about the attributes of the individuals if you're going to make optimal use of an understanding of network structure. Now this difference between the real impact of your real friends and the more tenuous impact of these weak online interactions was really driven home to me and James a few years ago, because very unexpectedly one day, a moderately well-known actress by the name of Alyssa Milano in the United States, who had 1 million Twitter followers, very unexpectedly send a tweet for our book, Connected: The Surprising Power of Our Social Networks and How They Shape Our Lives, with a link that if you clicked on that link, you went right to the Amazon.com website for our book. And that tweet was retweeted 1 million times that day. So on that day, 2 million people got a tweet with an embedded link to the Amazon.com website of our book. Now James and I, because we're neurotic, were following the sales rank of our book at the time. And so on the y-axis is the sales rank, and at the top is more sales, and at the bottom is fewer sales. And this includes the time period when Milano tweeted our book, and here's the day she tweeted. We estimate that we did not sell a single extra copy of the book, not a single one, despite 2 million tweets going out on that day. In fact, some people have looked at these data and said that when Milano tweeted our book, people raced to the bookstores to return our book, which explains the decline in that graph. So online networks facilitate interactions on a vast scale, though as we've seen, influence for many processes still appears to depend on face-to-face interactions. Online networks are very good for disseminating information, but not necessarily for disseminating influence or behavior change, unless the ties are realistic or unless something is at stake. So one way to summarize a body of literature that is growing by our labs and other labs around the world, studying how the online world works, is 3 little principles. One idea is that for online interactions to be efficacious in changing people's behavior, the interactions must be real or feel real. Either they have to really be your friends, or you have to cultivate a sense of these are really my people online. Second, something must be at stake. You can get strangers to affect each other online if they have a common purpose. We're both signing up to quit smoking. We're both signing up to manage our diabetes. We're both cancer patients who want advice about cancer chemotherapy. We're looking for a sexual partner. Whatever it is, that if something is at stake, people can affect each other online, even strangers. And the third principle is that people are obsessed with finding leaders, but you don't just need leaders, you also need followers. You don't just need shepherds, you need sheep. You don't just need influential people, you need influenceable people. So algorithmic ways of identifying cliques within the network that can identify influential people and also the people around them who are likely to copy those people are optimally required if you're going to take advantage of these online tools. So in short, there are 2 broad ways to intervene in networks to enhance public health and public policy or to advance business objectives. So now, given all I've just said, so we had an introduction to a little bit about the sociology and we skipped a lot of the mathematics of networks, a little bit about the biology. Given an understanding of social network structure and function, so what? What can we do with that knowledge to make the world better? And there's expanding science in this area. I don't have time to discuss a lot of it, but I'd like to summarize one experiment for you. Now, there are 2 broad kinds of experiments that we and others are doing. One manipulates the connection, rewires the network, assembles people into particular topologies, or assembles people into particular groups, attempting to change the structure of social interactions to see how that manipulation affects what happens to the group. So you take the graphite and you rewire it into diamond, you convert something soft and dark into something hard and clear. A second class of interventions accepts the structure of the network and instead tries to manipulate contagion, tries to change the flows in whatever it is that's spreading through the graph. And there's expanding science in both areas at the moment, advancing our understanding of how network effects might be exploited to improve the world, like improving health behaviors in the developing world, reducing smoking or increasing exercise in the United States, intervening in classrooms to increase seatbelt use or decrease bullying, intervening in the market to influence people's purchasing behavior, and so forth. Let me walk you through one paradigmatic set of experiments that we have been doing. Imagine you have 2 villages in the developing world, and we're doing this work in Uganda and in Honduras and in India. We're doing it in various places around the world. Imagine that you have 2 villages and you map the networks of the villages. And now imagine that you have just enough money to target 6 individuals, as shown in yellow here, with a public health intervention to get them, for example, to use a clean water intervention or vaccinate their children. Now, the classic public health paradigm is interested in what is known as the response to treatment among the treated. So you target these 6 people, you come back a year later, and you see that 3 of these 6 people have responded to your treatment. That's not what I'm interested in. I'm interested in the response to treatment among the untreated. I want to know what happens to everyone else in this village when you give these 6 people the intervention. So maybe you treat these 6 people, 3 of them adopt the intervention, but they recruit 3 of their friends, so a total of 6 adopt on this side. And maybe in the control village, only 2 of the 6, by secular change, also adopt. So that difference between 6 and 2 in this example gives you a pure measure of the spillover effect, of the externality that's induced by targeting particular individuals. But if that's true, it means you can begin to get very creative. So for example, instead of picking 6 people at random, maybe now you pick 6 people that are located in the center of the village. So same village, same intervention, same number of people targeted, totally different outcome. Now you target these 6 people, maybe 3 of them adopt the intervention, but they might recruit 30 of their friends compared to 2 in the control village. You might multiply by a factor of 10 the return on your investment by a shrewder targeting using a variety of mathematical algorithms of people who are structurally influential in the village. And we've been experimenting with a variety of mathematical algorithms for identifying structurally influential individuals. There are many different kinds, but for the present purposes, you can think about one algorithm as picking the people who have the most connections or who have the highest centrality in the network. And we've been doing one field site where we've been doing this work is in Honduras. This is the highland of Honduras, a coffee growing region. They're very poor villages, as you can see. These villages we work in have about 400 or 500 residents within the villages. And what we've done is we've mapped the networks of these villages. And in our initial project, we had a sample of 32 villages. And what we're going to do is in this experiment, we're going to take these 32 villages, and this third of the villages, we're going to pick 5% of the people at random and give them the intervention. And this third of the villages, we're going to pick 5% of the people who are the most central in the network, who have the highest in-degree centrality. And that third of the village, we're going to use, yet again, a different targeting algorithm, something we call nomination targeting, another mathematical trick to identify people who might be structurally influential. And then same fraction in all the villages, same intervention in expectation, same attributes of all the villages because of randomization. And now we're going to come and see where do you get the biggest cascades. So the questions become, how do we move a whole village and not just individuals to change their behavior? Given a budget constraint, who do we target? Who creates the most externalities for behavior change, and how can we exploit this? So here's one of my graduate students in the field, Allison Huang with a red hat, delivering, this is a clean water intervention. I'm not going to show you results from that. I'm just going to show you some results from a multivitamin intervention. On the x-axis is time, and on the y-axis is the percent adopting. The yellow bar at the bottom shows random targeting when you pick the people at random. The next step up shows in-degree targeting, and the step up from that showing the biggest bang for your buck using this nomination targeting algorithm that I didn't explain to you, but that's even better than in-degree targeting. So in fact, in this particular outcome, in this particular setting, in this particular village, we can get a 25% extra kick from nomination targeting compared to random targeting. And we have more significant, more substantially bigger results and many such results from many settings that we've been doing such experiments. So we can exploit ideas like this in 2 broad ways. Network science can be exploited in 2 broad ways. We can enhance, we can sort of turbocharge behavioral interventions both among the untreated and among the treated. So among the untreated, we can think about how to deliberately create spillovers. If you're marketing something to somebody, how can you do that in a fashion that maximizes the chances that others will also adopt? And second, we can deliberately exploit peer reinforcement to maximize the response to treatment among the treated. Are there clusters of people or other ways you can target individuals so that their positive behavior change is reinforced by the behavior of the people to whom they are connected? And we estimate that for a variety of public health interventions, we can quadruple the return on investment in some settings by taking into account network effects in various sorts of ways. People are connected, and so their health is connected, and we see this both observationally and in a variety of experiments I've shown you today experimentally. So now I'm going to close with a big idea, and then we have some time for questions. So the question remains, what's the point of a connected life? How does it help us as an individual and as a species? And it turns out that networks are a resource that we can all use. Networks are a kind of social capital. Now, most people, when they think about capital, think about money. But really, capital is any stock of resources that can be put to productive use. Capital is any stock of resources that can be put to productive use. And two further key ideas about capital are that in order to create capital, you have to invest skill and effort. You have to know something and do something in order to create capital. And second, and more subtle, and very deeply, that in order to create capital, one has to make changes in a substance that make it yield a higher rate of return than it otherwise would. Let me explain what I mean by that. So a farm is a form of capital. You can take a forest and invest skill and effort and clear the land and make a farm. And a farm is more productive than the forest, at least of fruits and grains and vegetables and flowers. And a farm is valuable because it's a source of productive power. It's a reservoir of wealth because you can do things with a farm that you couldn't do with a forest. So land, especially improved land, is a form of capital. Or consider this idea. You can take this tree, you can invest skill and effort and convert it into lumber. And the lumber is more valuable than the tree because you can do things with the lumber you couldn't do with a tree. Namely, invest still more skill and effort and transmute it into a violin. And the violin is more valuable than the lumber because you can do things with a violin that you couldn't do with a lumber, namely make music. So at each step of the process, you invest skill and effort, you endow the substance with new properties that it didn't have before, and it's those properties that make it a reservoir of wealth and a source of productive power. So capital is a change that allows the substance to act in new ways. And this is part of what makes it a store of wealth and a source of productive power. Now, in the 1960s, a number of social scientists, including famously Gary Becker and others, began to think about human beings in this fashion, began to think about human beings as a source of human capital. So here, for example, on the far left, you might take this dissolute former graduate student of mine who's a drunkard, and you can invest skill and effort and clean him up. And now he's more productive than he was before. He's capable of doing things he wasn't previously able to do. Or you can invest still more skill and effort and give him an education. You can change his mind. You can work on the neurons of his brain. And that's what makes him a reservoir of wealth. That's what makes him productive, capable of doing things he was not able to do before. Well, just like physical capital is created by a change in the material world, and human capital by a change in persons, social capital in organizations, companies, communities, and indeed in our whole society is a change in the relations among persons, a change that renders the group more productive and capable of doing things it was not previously able to do. And that's the deepest account I can give of why human beings form social networks, because in so doing we create a kind of social capital, and we have evolved to do that in ways that benefit all of us. Thank you very much. You're welcome. Thank you. I'm on Twitter if people are interested.
So we're just going to take some questions, and I'm just going to open it up to the floor. I'll just take a couple of questions at a time. There's a microphone here as well, so and then we'll let Nicholas have a go answering them. So who would like to open up our questions?
Have I stunned you into silence? No, good.
Yes, there's two. Would you like to start?
Good evening.
And this gentleman needs a mic too, right there. Yeah.
You mentioned that magic number of 3 in terms of the degrees of separation, but wouldn't you expect to see a difference whether the phenomenon is more something that is physical, like smiling, versus something that is more conceptual? Because one thing that distinguishes us from a chimpanzee is our ability to conceptualize and therefore to tell stories, and that's how we spread our networks.
Yeah, that's a good question. Should I answer that or take a second one?
I don't mind. Why don't we take 2 questions? Can you remember?
It's hard, but I'm going to try.
Okay, well, no, let's answer that one then, because I don't want to...
Okay. Actually, there's a famous British-American essayist called Bill Sapphire, who was a right-wing guy whose politics I didn't particularly like, but who was a brilliant essayist and wrote a column famously in the New York Times Magazine called On Language. And he was often appeared on talk shows, and as he got older, he began to find that people would ask him a 3-part question, and he would forget the answer to the third question. So he developed what's known as Bill Safire's floating third point. It was an optimized answer that could be used to answer any third question, so that as he answered the first and second question, when he got to the third one, he would have a stock answer. And that answer is, that answer to that question is, there are no easy answers. So actually it works like a charm. If you're asked a three-part question and you get to the third one, you go, and on the third point, there are no easy answers. And then you move on. Anyway, I remember your question, I think. It had to do with, yes, yeah. So actually different phenomena spread in different ways. And this is just a rule of thumb. Some things spread to 2, some things to 4. We don't yet have enough empirical knowledge, nor enough theory to guide us in predicting these things. So for example, I can't rank 50 emotions based on psychological theory and tell you which one will spread more than something else. However, by analogy, let me give you a point. After the Fukushima disaster in Japan, there was a lot of misinformation, rumors that were spreading on Twitter and on Facebook. Information about the extent of the contamination, the nature of the catastrophe, and so forth. And the Japanese government became very interested in this because it was a problem. People were getting horrible, false information. And we became interested in the issue of whether true information has different spreading dynamics than false information. Now, it turns out that false information, gossip, typically spreads faster and better than true information because the truth is boring, but the gossip is delicious, right? So you transmit it. So you would expect the spreading dynamics of false information to be different than the spreading dynamics of true information. And the challenge is, can you invent interventions to arrest the flow of false information and maximize the flow of true information? So the answer to your question is yes, you might expect from first principles things to spread differently, but the answer is also that we don't know yet any generalized rules about this phenomenon. Yeah.
It's just a comment really on one aspect of what you mentioned today. We're working with a diabetologist in East London that has a very high percentage of type 2 diabetics who don't comply.
Yes.
So what we're trying to do is to reach their relatives, both here and abroad, in order for them to exert some pressure on those guys and women to conform. We've had some success, but what I was interested in is the peer action. I don't see that this is spreading in any particular way, both here and abroad, and those other people are picking up on the obvious advantages of this interconnection, which is working with some instances, but not with many.
Yes.
And we wondered if the factor of perhaps having a maximum of 150 friends, which I believe is the human resource we have available, is coming into effect somewhere.
So there are many people experimenting with these effects right now. So people are developing apps, for example, so as your patients finger stick themselves, their glucose is recorded, and then they can enable their friends abroad to monitor and say, oh my goodness, here's your finger stick glucose, let me call up mom and tell her to manage it better. You can bring these diabetic patients into the doctor's office and introduce them to each other like Alcoholics Anonymous to create support groups. Or you can interconnect them online so they can reinforce each other's behavior. The problem is that there's no rule of thumb for this. So for example, you could bring a lot of non-compliant diabetics into an online platform, and the guy who had a sugar of 250 before might look around and say, all these other guys have 400. I'm doing great. I'm not going to make any effort. So remember, networks magnify whatever they are seeded with. They're agnostic. So in addition to bringing them in, it's not just enough to just throw them together. You have to pump the system with effort to improve their diabetic management. And if you couple that with thoughtful mathematical manipulation of the social interactions, you can in fact encourage desirable behavior. I didn't show you some experiments we've done today. I didn't have time, but we've done some experiments to examine different ways of assembling groups to reinforce desirable behaviors. So I guess I hope am I answering your question?
Well,
Not
it's
really?
more complicated, isn't it, than I may have made it seem. But it does appear that...
It was plenty complicated from the way you made it seem already. Don't have to make it any harder. I'm at the limit of my ability right now. Sorry, go on.
The point you made about having something which is relevant to somebody else's blood sugar levels seems to be predominant. In other words, if you're seen to have a lower blood sugar level, although it's nowhere near compliant, you're seen to be doing the right thing, and therefore there's no need to do any further work. Now, the way in which one can influence the group to take that on seems to me to be very limited, and we've had no success with that kind of crowding of ideas.
So I mean, there are people, I don't know exactly what you've done, obviously, but there are a number of people around the world that are doing different sorts of experiments. So one thing that's been done, for instance, is, let's say you have $100 and you've got 10 people and you're trying to get them to quit smoking. You could spend $10 on each of them individually, and maybe you persuade one of the 10 to quit smoking. Or you could bring all 10 of them into the doctor's office at the same time, give them a group level intervention, and spend $100, same people, different intervention, same amount of money. Now you might get, of those 10, 3 or 4 people to quit smoking by exploiting positive peer reinforcement in that regard. So people are working on this. People are trying to figure out ways. And their successes and failures, I don't have time to go into today. We have a review if you're interested. If you just Google Christakis and social networks and health, you'll find some reviews looking at some of these ideas.
More questions? Yes, one here and one here. We'll take one at a time, I think.
Thank you very much. Very interesting. I got stuck on your obesity wave.
Yes. That was early in the talk.
Yes, I'm still there.
Catch up, man, catch up.
And it also relates to the question that was asked earlier about different things playing in, producing different effects at different speed, all at the same time. You said that it's difficult to see the wave on that network, an animated network. And I imagine besides obesity thing, there is also spread of ideas, there is spread of happiness or unhappiness, there is several factors that played into network. Did you manage to decipher what was going on beneath? What factors played into behavior on that network? Because if you can do causation, you can then predict.
Yeah. So we looked at, if I've understood your question correctly, we looked at a number of possible deeper possible explanations for the spread of obesity. So for example, was it a spread of eating behavior from person to person? Or smoking cessation behavior? We know that if people quit smoking, they gain weight. We know that in the time period of that network, American smoking rates were declining. Maybe what was happening is people were copying each other's smoking cessation behavior. And we looked at a variety of other clues, which I didn't go into, that helped explore the question of this normative explanation, that is, you change your ideas about body size. And we found evidence for multiple such things. So I don't want to go into it because it would take a lot of time. It's in the paper, if that's what you're asking. So so it's not like by magic, it's not like she gains weight and I just poof, explode. I look at her and then I either, for example, she might say, Nicholas, let's go have muffins and beer, which is a terrible combination, but I like Amanda and she suggested it. So I adopt her terrible eating practices. So you can actually tease out some of those effects. Is that what you're asking?
I was interested how much variability you managed to explain by digging deeper into the sources.
It's an observational study. People have, since we've done that work, a lot of people have done experimental studies where they've controlled very tightly what the intervention is to look at, for instance, if we give a man a particular diet, what happens to his wife's weight? So we now know that we randomly assign, you women get one diet, you women get a different diet, and we don't weigh you, we weigh your spouses, and then see what happens to your spouse is conditional in the diet we give you. So people are beginning to drill down and look at some of the potential mechanisms.
Yes.
Thank you, that was great. Can I ask you a question about this issue to do with obesity? Part of what you're saying is that obesity is a bit like an infectious disease.
Yes.
We produced a report in 2007 which said that obesity since 1980 is the consequence of better marketing of food and people eating more calories basically as a consequence of that. And the desire to get people to eat more, basically, in a commercial sense. And a load of people come up and said, look, we've read this guy, Christakis, in Yale, and he's sorted us for it. It's nothing to do with that. No. It's all to do with being an infectious disease. And they produced lots of mathematical models which talked about it being an infectious disease and could explain the same phenomenon. So my question is, if it is, why did it only happen after 1980?
Yeah, so let me just say there's a lot I want to say there. So first of all, we are not saying that the network spread of obesity is the only cause of the obesity by any stretch of the imagination. There are many causes. Remember also, the network alone doesn't give rise to the obesity epidemic. Something else, like the marketing of food, may impinge on the network, and then the network takes off. And this is going to require me, your question plus one other person's question is going to require me to go on a slight digression, which is a bit off color, but I'm going to do it.
What do you mean off color?
Well, it's what we use in American English. I'm just going to tell you the story. So imagine you have 2 islands in the Pacific, and on this island there are 100 people, and on this island there are 100 people, and on this island everyone is having sex with everyone else. That's what I mean by off color. So everyone is having sex with everyone else, and on this island nobody is having sex with anybody else. So in network terms, this is a fully isolated graph, And this is a fully saturated graph. But in neither island is there an epidemic of STDs, of sexually transmitted diseases. They're both fine in their worlds. Now a sailor washes up onto the shore and has sex with one person. Which of the two islands do you get the bigger epidemic of STDs? The first one. So the structure of the network is highly relevant to the magnitude of the epidemic, right? And this is an extreme example of fully saturated and totally unsaturated graph. But the network must be seeded. Prior to the sailor, there's no epidemic of STDs, right? You have to seed it, then the network kicks over. Okay. Now imagine that you have an island on the Pacific, everyone is having sex with everyone else, here everyone is having sex with everyone else. Now here everyone is immunocompetent, and here everyone is immunocompromised. Their immune systems work, their immune systems do not work, okay? But the structure of the graph is the same in both, fully saturated in both. Now a sailor washes up on the shore and have sex with one person on each island. Where do you get the bigger epidemic now? Yeah, where they're immunocompromised. So this goes back to the Love Actually example. It's not just enough to know about the structure of the network, you need to know about the attributes of the individuals within it. In this network where people are immunocompromised, you get the bigger epidemic. And now picking up on the question of the woman behind you, now imagine that you have an island here, everyone's sex with everyone else, everyone's sex with everyone else. Now they're both immunocompetent, okay? And I'm going to tell you a piece of biology some of you in this audience will know, others will not, which is that if you have sex with someone who is actively HIV positive, per sexual act you have about a 1 in 500 chance of getting HIV. So you don't get it for sure if you have sex even with someone with active HIV. It depends on what sex act and a bunch of other things, but roughly speaking 1 to 100 to 1 to 1,000 risk per act. Now if you have sex with someone who has active syphilis, your chances are about 1 in 3 of contracting syphilis. Okay? Now, a sailor washes up on shore here, he has syphilis. A sailor washes up on shore, he has HIV. Where do you get the bigger epidemic? Syphilis. So it's not just the structure of the network, it's not just the attributes of the individuals, it's attributes of the thing itself, going back to the question behind you, that also matter in whether you get an epidemic. Now in the case of pathogens, we have 100 years or more of science, since Virchow at least, to help guide us in understanding which pathogens are more spreadable. The spreadability of a pathogen is different than its lethality. It's like the quality of a movie, it's different than its spreadability. You might see a movie you love and not tell anyone. You might see a movie you hate and not tell anyone. Or you might see a movie you love and tell everyone, or a movie you hate and you tell everyone. Those are different properties. Similarly, HIV is much deadlier than syphilis, but it's less spreadable than syphilis, right? So, whereas with pathogens, we have 100 years of biology to help guide us. How big is it? How hydrophilic are the proteins on its surface, etc., to guide us in making predictions about the spreadability of a pathogen. When it comes to other sorts of things like obesity, happiness, and so forth, we don't have the same foundation of science to make those predictions ex ante. So, in response to what you were saying, what I think is happening there is our society is doing okay until the 1980s. Then the marketing of food takes place. If we were all monks when that happened, all of us would have gained 5 pounds. But since we're interconnected, we all gain 20 pounds. The network magnifies whatever it's seeded with. Did I answer your question? Yeah. Good.
Okay. We have one person here. And then we need the mic down here as well, please. And then we've got another.
I'm going to reserve. I was hoping one of you would ask me a question that would give me opportunity to use an extra set of slides I have. And if you don't, I'm going to reserve a minute to myself to just show you that anyway. But yeah, next question.
I'm going to disappoint you.
Maybe not. Maybe this will be the lucky lotto, and you'll always have bing, 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 and I'll show you the slides.
You said that networks look the same now as they did 10,000 years ago with the example of the African tribe.
Yes, but I don't want to essentialize the Hadza. I mean, they of course are modern people. They just live like we did 10,000 years ago. Yeah.
What I'm kind of interested in is that tribe, I presume, is fairly egalitarian of one ethnic group, whereas modern societies are very inegalitarian and are very multi-ethnic.
Yes.
So is the similar network patterns because we all keep to ourselves and our own ethnic and social groups, or because these ethnic and social groups actually aren't as important as we might think they are?
So, so I'm going to reframe your question a little bit and say you're asking a very deep question about ethnocentrism, about in-group and out-group biases, about the plurality in modern society. Keep in mind that the networks we mapped, I didn't show you, we've used sort of NSA-type metadata for a whole European country, 8 million people, and mapped the network of those people, many ethnic groups. And their networks look the same as Hadza networks too, even with inter-ethnic ties. But the reason I blew by some of that stuff is because if you see an American diabetologist studies diabetes in American rats, and a French diabetologist does so, you don't ask them, well, those are American rats and those are French rats. You think there's something fundamental about the rat pancreas that is independent of which genre of lab rat is being used. And I think similarly about human sociality. I recognize that there's an enormous amount of variation. If you go to Saudi Arabia and you look for male-female friendships, you're not going to find any because of the important overlay of culture. But what I'm interested in is the deeper, fundamental, relatively invariant, universals, social human essentials, human nature, that's relatively the same everywhere. And that's mostly what I'm after. I'm trying to understand that. What is our deep sociality? How are we still bound by it? Now, of course, you can manipulate it. You could, go to a British boarding school, for example, which will really screw with your social networks. There are all kinds of things that you could do. But I'm interested in the way in which networks are invariant or less impervious to those types of effects.
I'm afraid we're going to have to take one last question.
And then I get a minute, right?
Yeah. And then you get a minute. If you want your minute, one question.
Okay, my question's not about obesity. That's a bit too close to home for me.
So, ditto, brother.
Yeah. I like the idea of the villages more. I'm wondering about centrality and how centrality operates. So in hierarchical systems, centrality may be a result of position, but in other social networks, it may be a degree of influence and so on. If you're saying that it's better to have a phenomenon diffuse or go through the network by saying 3 people in the village, is it more important that they're located in the hierarchy or that they're informal influences?
Yeah,
and does it make a difference? The nature of centrality is the point I'm getting at. Is there a difference in the nature of centrality?
So I have 2 answers to that. First, people who've looked at organizational networks and have looked at like the org chart of an organization, the kind of formal hierarchy, and then used email traffic to map the network communications in the thing, find that they're very different oftentimes. And there are different ways of approaching an understanding of an organization, but a lot of the work gets done based on the network structure, not based on the hierarchical structure. Now that doesn't mean that if you don't go to the chief executive of an organization, nothing will happen. I don't know what you think about your organization, but often, you can get things done if you're the dean. But sometimes not, because you've got intransigent bureaucracies, you've got department heads that have their own, you've got faculty in this department that are just locked in, and are not going to blah blah. So there are different ways of approaching it. The question is there a collinearity between structural position? For example, is it the case that the central people are more educated or taller or more charismatic or have different personality traits? And could those be used as a proxy for the tedium of mapping the network or other ways of identifying central people? And the answer is partially yes. So network structure has something to do with formal structure, something to do with institutions, something to do with the attributes of the individuals, but not wholly to do with any of those things. And you get an extra bang for your buck when you map the networks. Okay, I'm going to show you one last thing because I can't resist, and then if you have more questions, I guess I'll be outside and can talk to you.
There's drinks outside after.
Okay, so I blew by, I used the word emergence once in my talk, and then I talked about the famous example of carbon as an example of this idea of emergence. Emergence is the idea in science that the whole has properties not present in the parts, that the whole is greater than the sum of its parts. It's a very deep and interesting idea that all branches of science have been wrestling with, especially in the last couple of hundred years. And I'd just like to show you my favorite example of emergence, other than the chemical example, from biology. So this is one of the simplest organisms on the planet. It's an amoeboid fungus called a slime mold. It's very, very primitive. And what this organism does is it lives on the forest floor and it digests cellulose. It finds dead wood and it digests it. And little individual cells of this amoeboid fungus fuse with nearby cells and they make a kind of a superorganism. They assemble themselves into a network. And if you grew up in New England, and I don't know if this is the case in the fall in England, when you lift up wet leaves, do you see those little white tendrils in this country under the wet leaves? Do you know what I'm talking about? Yeah, those white tendrils are what this fungus does. It forms these little networks, these little tubes. If you lift up those leaves, you look, it looks like a pretty network. It's a 2-dimensional fungal network. It has certain interesting properties, but anyway, it's forming a network, and it's foraging for dead wood on the forest floor, bringing the nutrients to the center and distributing the waste to the periphery. If I asked you if this fungus was intelligent, you would look at me and say, what are you talking about? How could this fungus be intelligent? For example, if I said to you, could this fungus solve a maze? You might say, what are you talking about? Well, here is a project done by Toshi Nakagaki, a Japanese mycologist, where he took this fungus and he plated it on a maze, and at the entrance and at the exit to the maze, he put some oat flakes as a source of cellulose, and he plated the maze with fungus, and he let the fungus do what it does. Oops. Yeah, so here is the fungus now assembling itself. The fungus is fusing with its neighbors, and you're going to see the whole plate of fungus fill. Here's the entrance and the exit. And all the paths through the maze are going to die back, except the one most efficient, shortest path through the maze, highlighted in red. This fungus is better able to solve mazes than Toshi's graduate students. Actually, not better than my graduate students, I told him. And so this maze-solving ability is an emergent property of the fungus, right? Just like the softness and darkness and hardness and clearness, just like the social capital idea about human social networks. And this type of maze-solving property of the funguses has been used in a variety of ways. They are able to evince a kind of cellular computation, a kind of primitive intelligence. And this led my colleague Mark Fricker, who's a British mycologist at Pembroke College at Oxford, to do the following experiment. He took a map of England and he put an oat flake at every city, and he let the fungus do its thing and create a network of England. And then this was then showed to British railway engineers, and this is the railway network in England made by British railway engineers over the last 150 years. And when they saw this network, they said, oh my God, this is incredible. Because actually the fungus figured out where to put trunk lines and do other sorts of things that were weight balancing and that maximized the efficiency of the railway network in a way that these human beings had not been able to accomplish. So this resulted in poor Mark, a humble British mycologist studying fungi, being appointed to Her Majesty's Commission on the Rails. So he's now advising railway design. Thank you very much.